Okay, it's 11:30, 1:30. Okay, there's a summary of what's coming next, what that's worth. So I wanted we after thinking about Pali state transfers, you've got a point here and a point there, and you want to move from A to B. But what I'm doing now is I'm adopting a more geometric view of what's going on. So I'm thinking more about the path followed as you go from state A to state B, rather than just the individual steps. And so it's kind of background. I need to make some remarks about group theory. So the first thing is that we've defined the transition matrix U of T is here. Now, physics will have a minus sign there, but that makes no difference, because, in particular, because our Hamiltonians are symmetric, and so it's you can do either way. And so we have this set of unitary matrices. Okay, now that's a T there, not an E, but we won't worry about that. So the point is that is a group. U of S times U of T is U of S plus T, and U of minus T is the inverse of U of T, and U of 0 is the identity. So this is a group. In fact, it's a commutative group because, well, it follows one of it. Say that the map that takes a real number T to U of T is a homomorphism from the reals to the group of D by D unitary matrices. Now, I can't just, I'm inclined as a group, some sort of a group theorist, I would normally use something like UDF to denote the unity group of D by D matrices over the field F. But I was scolded once by a physics referee who was upset that I was writing UDF and said, what could F be but the complex numbers? Well, as far as we're concerned, it's only the complex numbers, but it could be other things in general. Anyway, so we have a homomorphism from the real numbers to the unitary group, and so now in operator theory, they usually refer to this. Well, they only in the values where T is non-negative, and then they'll refer to this as a semigroup. Technically, it's a monoid since the identity's in there, but they would call it a semigroup. So if you look at the books on operator theory, you'll see at some points they start fussing about semigroups, and this is the same setup. Now, so since the reals are an abelian group under addition, and since this U of T is a homomorphic image, this again tells you this confirms that this is abelian in case we doubt it. Now, there's some other homomorphisms around which I want to spell out. If Z is an eigenvector of the adjacency matrix with eigenvalue theta, then UT applied to Z, is equal to e to the IT theta Z. So point is the eigenvalues of U of T, things of the form e to the IT theta, okay, where the thetas are real for us, okay. So these lie on the unit circle, okay. So the point is, actually, you don't see it so much when you just work, here's a matrix, what are some eigenvalues. If you're working with algebras or more general collections of matrices, the map from matrix to eigenvalues tends to be a homomorphism. Because if theta is an eigenvalue of A, then it's an eigenvalue of A squared, and there's provided everything commutes, you get a homomorphism. Now, let's not worry about that. But the point now is that if you've got, once you pick your eigenvector, you have a map from U of T to e to the IT theta. And so this gives you a map homomorphism from U of T to the unit circle in the complex plane. So now we have homomorphism from T to U of T, and then a homomorphism from U of T into the unit circle. Now the unit circle in the complex plane is itself a group under multiplication. Okay, and of course, since it's a homomorphic image of U of D, it has to be an abelian group, but that was not a surprise anyway. So this is just a group of rotations of the circle, if you want to think of it that way, rotations and reflections. The group formed by the unit circle complex plane is, with no originality, called the circle group. It's often, it's a quotient of the reals. Okay, you map the reals to the unit circle. Okay, now you the reals are not a compact set. The unit circle is compact, so you must lose something. Anyway, so it's a quotient of the unit circle, and so it's common to say that R over Z is the circle group. So and so this is just the quotient. So this is the image of R, and homomorphism takes the integer vectors to integer numbers to 0. More generally, if gamma is a non-zero real number, then modulo gamma Z is isomorphic to the circle group. And so I'm probably going to be sloppy and just refer to something as circle group, provided it's isomorphic to the circle group. Now, so what I've told you is that I've constructed a couple, or shown you where there are some homomorphisms hiding. Do I? Yeah, it's coming. The one result which I need, which I'll be using, is that any subgroup of the reals or of the circle group is either discrete or dense. So that means either it's just integer multiples of some tau, okay, or every point of the real for every point of the reals and every epsilon, there's an element in the group which is within epsilon of your real number or your R1Z. I mean, this is just basically a reasonably straightforward analysis argument. You basically need, you need the fact that, that a good test case is just to prove that the subgroup of R generated by 1 and √2 is dense. Okay, I may even put that in the assignment. It's not entirely fair since we're not going through the number theory, but that would be essentially, if you prove that, then you can prove the general case. So it's not particularly deep, but it is useful. Okay, and so my attitude is this number theory is there to be used. I'm not going to fuss too much about whether I've gone through the proof of it or not. But in this case, it could be done. But so the important thing is that the subgroup is either discrete or dense. Now subgroups matter because we just go back here. We have a homomorphism. Actually, I think, oops, where is it? We have a homomorphism from the reals to U of t. And so it's a very natural question and a useful, important question. What is the kernel of this homomorphism? Well, it's a subgroup, but by your group theory. And by the result I was just talking about, this subgroup is either discrete or dense. Now, if it's discrete, then the image is essentially the circle. Well, it's a discrete cyclic group. Okay. If it's dense, it's not quite clear at this point. But so the point is that that's important information in understanding these maps. Now, the set of unity matrices U of T for T and R is a subgroup of U to D, as I said before, and it's often referred to as a one-parameter subgroup of U of D because it's indexed by one real parameter. There are multi-parameter subgroups that we don't actually. No, I'll back off. So there's a one-parameter subgroup. A one-parameter subgroup just means a homomorphic image of the reals. So you have a homomorphic image of reals into some other group. We're concerned with the unity group. It could be the orthogonal group, the symplectic group. All these things are reasonable. But you have a one-parameter subgroup of the reals, and these subgroups are quite important. They, in a certain sense, if you understand how these work, you can understand the entire unity group U of D without too much trouble. The other thing to bear in mind is that, okay, so you can think of this as a curve. So you've got the unity group of D by D matrices, and this set you're picking your real mapping from real numbers to U of T, and it's going to trace out a curve on this surface formed by the unity matrices. Technically, it's a manifold. Okay, so it traces out a curve on the manifold. Okay, now the issue is that's a nice curve. It's continuous. It is not necessarily a dense. It is not necessarily a closed subgroup of the unity group. Now, closed subgroups of the unity group are nicer to work with because there aren't as many. There are, in some sense, very few of them. But so the example, and I'm not sure if I can draw this properly, but I'll give it a try. Is to think about a curve on the torus. Now you can think of the torus as being the R2 modulo Z by Z. So it's actually a direct product of circle groups. Now, the way I think when I'm doing it, suppose the torus is an image of the plane. Okay, so you can view the torus as a quotient group of the plane. Now, what I'm going to do is in the plane, I'm going to look at the points, integer multiples of the vectors 1, root 2. Now, I look at the entire line spanned by 1, root 2. Now, if you think about it, when you curve, well, you need to think about it a bit, but when you map the plane onto the torus, that curve gets mapped onto a dense curve on the torus. So every point in the torus, given an epsilon, each point on is always a point in the torus within epsilon of your chosen point. So it covers the entire torus, okay, in some sense. Okay, and so what's happening there is that I would say that the image of the curve is not is not closed. It's a dense subgroup of the thing. Now, so you just need it. Well, it's an important difference and underlies some interesting phenomena in terms of quantum walks, which we might get to later on. Okay, so there's a problem here. Now, the other comment related to these homomorphisms, we have that U of t is given by e to it theta r. So the ERs are determined by the graph. Well, theta r is too, but we're not going to work at this beside the point now, but the ERs are determined by the graph. So U of t is determined by the points theta 1, theta 2, up to theta m. Now, the point is that this, do I want to put t in there? Well, no, this is fine. So if you give me theta 1 through theta m, I can write down the eigenvalues e to it theta r, and so I can write down U of t. Now, and so we're getting a homomorphism from the thetas to U of t. Now, the thetas would generate a subgroup of the reals, but we're going to be taking everything mod 1. So this is this group is a, well, technically it's called a torus, and it's a direct product of circle groups. So this is more general homomorphisms been talking about before, but my point is I'm looking at U of t, what we're seeing is a homomorphic image of this group, which is a direct product of circle groups, which is not particularly, well, it depends on your point of view, I guess. It could be a lot worse, let's just put it that way. It's a bit more complicated than you fit. Because of this problem about whether you're dense or not, there are some issues you have to think about from time to time. But it's an abelian group, and each factor is just a circle group. Okay, and so it's reasonably straightforward. So we have, and the point I'm trying to make here is that can't resist. The point so well, U of t is a direct product of isomorphic to a product, or homomorphic image of a product of circle groups. Okay, now. And continuing with this, okay, I was saying U of t is a group, and groups tend to act on things. Well, I'm going to define an action on the space of density matrices. So if D is a density matrix, then this set is what people have got theory call a forward orbit of U, the group of unitary group, acting on a set of density matrices. So you pick D and then you compute UT, D, U to the minus T for all T. And so you've got think of it as a curve in the space of density matrices. Okay. And so for example, it then follows that you have perfect state transfer from D1 to D2 if D2 lies on the forward orbit of D1. Now, because our Hamiltonian is symmetric, it happens if D2 is on the forward orbit of D1, then D1 is on the forward orbit of D2. And so we don't, for our purposes, we don't need to distinguish between orbits and forward orbits, but the orogonic theorists have to pay more attention. So we often dealing with situations where only the forward orbit would make sense. And that's the terminology we're using here, but for us, it's an orbit. And so my point is that questions about perfect state transfer and things close to perfect state transfer can often be translated into questions about these curves on various places, and that this can be very useful. There's not much detail that you need to think about, but just to be aware in mind, we've got various groups sitting here. We've got the real numbers, we've got the unity group, we have our one parameter subgroups, we have the circle group, we have the direct product of circle groups. So these are all there, and you can use them from time to time. Okay. Any questions at this point? Okay. I mean, you don't need to worry too much about that stuff because I won't be asking you any questions. Very few questions about it, except perhaps for that one about dense subgroups. Okay. Now for the next section, what we're thinking about, well, we've talked about periodic walks. Okay, and we've seen they can happen. So if the eigenvalues of the graph are integers, then the walk is periodic. Okay. In general, the quantum walk is not periodic. Okay, it doesn't converge to a steady state. It's not periodic. It doesn't have any redeeming social qualities, well, almost none. Okay, so it turns out it is trying very hard to be periodic in general, and that's what I want to talk about. So, so the result is, assuming we have a continuous quantum walk on X with transition matrix U of T, and assume tau is positive, real, then for each epsilon greater than 0, there's an integer k such that UK tau minus the identity, or the norm of UK tau minus the identity is less than epsilon. Okay, and so the point is, when you think about your trajectory, the orbit, so U of 0 is the identity, and what this is telling you is if you pick an epsilon, I can find a k such that U of k tau minus is within epsilon of the identity. Now, something stronger is actually true. It actually implies that if the walk visits a certain state, then it will return to within epsilon of that state infinitely often. I'm just writing this down for the identity. So the issue is that this is looking a lot more like a periodic work. It is trying to return in a certain sense. And now, in fact, a somewhat stronger statement is true, and I'll talk about that later on, but this is the only one I'm going to prove for now. So the point is that the walk returns, okay, you get to choose an epsilon, I can find a k which takes me, so it's a k times tau. And of course, tau is a variable too. So for the purposes of this argument, you can just take tau equals 1. It doesn't really matter. Okay, so we're looking at the, so if you take tau equals 1, you're looking at this, U0, U1, U2, U3. These are just the powers of U1. Okay. So the proof is not that complicated, provided you're used to compact sets. So we'll see how it goes. So I'm going to consider the sequence of, I just mentioned, identity, U of 0, U of tau, U of 2 tau. So this is just a sequence of powers of U of tau. Now, if this sequence is periodic, so if there's some m such that um tau is equal to identity, we're periodic, don't have anything to prove. So I'm only concerned about the case where it's not periodic. In that case, if it's not periodic, this sequence must have an infinite number of distinct terms. It can't actually have 2 repeated terms, because if it has 2 repeated terms, you can shift back to the origin and you'll get the recurrent. So you can argue you have an infinite sequence of distinct terms. So you've got this infinite sequence sitting of matrices in the d by d unity group. Now, the d by d unity group, you look at d by d unity matrix, each row and column, it's got norm 1. So the unity group is a compact subset of a set of all d by d matrices, or d by d complex matrices. So now you have an infinite sequence of points in a compact set. Okay, and so then the argument is, I don't even remember the name of the theorem now, it doesn't matter. That tells you that this sequence has a limit point in the space of d by d matrices. Now, I'm not saying that there's a limit point, that one of these terms is actually the limit point. I'm saying there is a limit point So there is a point, I call it t, and so what we're saying is that, and so definition limit point says that for every epsilon, the ball of radius epsilon about t contains infinitely many terms of the sequence. Now, this sort of argument is a lot easier than working with epsilons and deltas and things. Okay, so it's a bit more conceptual. We're saying we come back, we've got a limit point. So the idea is to work with limit points and definitions limit points and compactness rather than trying to prove things using epsilon delta. So we've got this limit point I'm calling t, and the t is not in the sequence, but it's in the closure of the sequence because every ball of radius epsilon about t contains a point of the sequence. So, and the example to think of is the my sketch of a drawing for the torus before. The t is going to be a point on the torus. It may not be actually on the curve, but the curve is going to get close to it. It's going to get close to it infinitely often in some sense. Okay, so we have the limit point now, and so any ball of radius nu about t contains two distinct points of our sequence. Well, it contains infinitely many, so it contains two. And so let's say that they're u of k tau and u of l tau. Then by the triangle, so u of k tau is within epsilon of t, and u of l tau is within epsilon of 2 t. And so by the triangle inequality, the norm of the difference between l tau and k tau is less than twice u. So they're both within epsilon of t, so they're both within 2 epsilon, within the 2 epsilon of each other. Okay, now because we're u is unitary, it preserves the norm, and so we can pull out the u to the k tau, and then we're looking at the norm of this. So that's telling us that u of l minus k tau minus the identity is less than 2 nu. Okay, and so you just choose nu to be anything less than half epsilon, and you get the theorem. Are there any questions about this? Okay, so a couple of comments. This could be viewed as an instance of what's called the Poincare recurrence theorem. Let me just. That's a more general result, but the proof is not too far, quite close to what I've just done. So now the Poincare recurrence theorem is, well, Poincare was thinking about orbits of planets and things, but he was doing physics. The problem with the Poincare recurrence is that you don't have much control. We know that we're going to return to within epsilon of the identity. We don't have much control over the time it takes. Okay, and in practice, the waiting time is not physical. It starts getting comparable to the life of the universe or something. Okay, but as a mathematical theorem, we're okay. And as I said, Poincare was doing physics when he came up with this, and there's a lot of statistical physics where they're using this sort of thing. But if you the waiting time, the return time can be very large. Now, if you look in the notes. Look, in the first chapter, we work out some properties of the quantum walk on P4, and you'll see something similar there. Okay, it's not recurrence time; it's dealing with pretty good state transfer. But if you look at the arguments, you'll see that thing. So we get something like PST on P4, but you've got to wait a long, long time. Okay, now that's the first comment. The other comment is a slightly stronger result. So this is like saying if you have a random walk on a line, you return to the origin, but the average return time is infinite. But that's not what's going to happen in this case. So in fact, there's a slightly stronger result. If you give an epsilon greater than 0, there's an integer DL such that each sequence of L plus 1 terms contains a point within epsilon of identity. So in other words, not only does it return infinitely often, but it returns at least once in each interval of length L. Now, L will be very big, okay, but the point is it does return. This is called almost periodicity. And this is discussed in the notes too, if you care. But where I'm just saying that, okay, there's the basic point is that if a continuous quantum walk visits a state, then it returns to within the epsilon of that state infinitely often. Okay, so in a certain sense, it is trying as hard as it can to be a periodic sequence, but doesn't quite make it. Okay. And this is just repeating what I just said, that there's nothing particular special about identity. It's true for any state that if it visits a state, okay, then it must return within epsilon of that state infinitely often. Okay, any questions about that? So this is that's an important qualitative property of continuous walks. Okay, and so now, so we've been talking about periodic vertices. Well, back up a little bit. We saw that if you have perfect state transfer in a continuous walk, then it happens within time. Well, let's just say 2 pi. It's a little bit less than that, but that was within time 2 pi. So we have an upper bound on the time. But we also have an upper bound on the time to return time periodicity. Okay. What I want to do now is look at the other end and ask, what is how small can the period be? Okay, and we're going to get a bound which is not tight. It might be tight once. It's not tight, but it doesn't seem, it's not completely ridiculous, whatever that means in mathematical terms. Okay, so we're trying to get a bound on the minimum period. So we assume we've got a periodic vertex in a continuous quantum walk on X. Okay, and I'm going to define per of A to be the set of times K such that, well, return times. Okay, except now we're calling them periods. Okay, so that's a set of times. It's well defined, and the assumption is there's at least one non-zero element in pair of A. And the lemma we're going to prove is if you have a periodic vertex with of X with valency which is not isolated, so it's got valency at least 1, then there is a number tau such that the periods are just all integer multiples of tau. Okay. Now that tells you that there is a minimum period. Other than that, it's not particularly useful in terms of, if you ask me what would the minimum period be, this is not helping me, but it tells me there is a minimum period. And we'll get a lower bound in any case. So, so we're getting the existence of a period, and it's using the sort of group arguments I was talking about earlier. The key point is that the periods form an additive subgroup of the reals. If nu is a period, so is minus nu1 plus, if nu1 and nu2 are periods, then nu1 plus nu2 is a period. It's an additive subgroup of R. So there's 2 possibilities. It's discrete or it's dense. Now, the discrete case is just saying if it's discrete, then A is periodic, and we're assuming that's not the case. Actually, I'm assuming that. So with A is periodic. If it's discrete, we get this. Okay, so discrete means that there's a scalar delta such that any 2 elements of pair A distinct elements differ by at least delta. Okay, so periodic is what we want. So what about the dense case? We have to try and throw that away. And so the argument is if the period of that set of periods is dense, then we can find a sequence of times, periods with limit 0. Okay, so we have a sequence of times with limit 0. Now, since U of tau is differentiable, you discover that, well, this converges to the derivative of U of tau at 0. And the derivative of U of tau at 0, do I really want to minus in there? What do you think about that? No, I just want to, it's not going to play any role anyway. Physicists would have a minus side. Okay, so the important thing, okay, so it's just the adjacency matrix. So just to remind you, in fact, so the derivative I should say the first place where you might run into matrix exponentials is when you're solving linear differential equations. And the fact that the exponential gives you the solution to the differential equation without the fiddling around that you see in the first course, and that's an A. And so we have x of it, so we pick up on it. You got that right. Okay, so we have that. Now, assuming that t is a period, the point that tells me u of t is commuting with this projection. This is a projection because this is a projection, okay? And well, by one argument that will do, and that then implies that the space spanned by E sub A is invariant under view of t. In other words, E sub A is an eigenvector. So by one means or another, you prove this, okay? So E of A must be an eigenvector. Now you've got, okay, let's go back to my blue again. You've got an eigenvector, well, we can assume it looks like it is. Now, the point is if, and by this limit calculation that we've just done, it's also an eigenvector for A. Now, if this is an eigenvector for a adjacency matrix graph, then this vertex must be isolated. By the adjacency matrix of this, you get the first column. Okay, so if and so then A is an isolated vertex, and we took care of that by hypotheses. So we include the period of A is period A is discrete, and the lemma follows. Okay, so this is okay. Any questions at this point? So this lemma implies that the minimum period exists, and we now get a lower bound in 2 steps. Okay, so assume X is a graph with eigenvalues theta 1 down to theta m in decreasing order. So I'm assuming that there are exactly m distinct eigenvalues, and assume that C and D are density matrices, and that the trace of P times Q is 0. And then the claim is we have transfer from C to D at time t, then t is at least equal to this. Okay. Now this is kind of intriguing because you see this difference here. This is the sort of difference we saw in our ratio bounds, and so it's interesting that it appears. I don't know of any concrete connection, but it still intrigues me. Okay. The other point is that if let's look at the case. I'm writing this out in general, so I'm just picking 2 density matrices. I'm not assuming even that they're real; they're just density matrices. But I do want to note that if this is 0, if A is not equal to B. So you'll get a pair of states like this every time you have steady state transfer. Okay, between 2 vertex states. Okay, but we don't need to worry about that. All we need is that these are density matrices, and in that case we get this lower bound. Okay, and as I said, this is not tight, but it's not ridiculous. So the since C is posi-semi-definite, it has a unique posi-semi-definite square root. C is equal to unitary matrix times the diagonal matrix on negative entries times inverse unitary matrix. The diagonal matrix on negative entries has a unique positive square root. Okay, and so we're going to be original and denoted by C to 1/2. Okay, now the assumption is, well, we're going to be assuming that this is going to be D, and so this is going to be 0. But we're not there yet. We're doing some preparation. Okay, so this part's going to turn into 0. So we've got this inner product. Okay, now we're just working from there. So that's just the trace of this mess. Okay, well, I'm just taking the trace of C times that. And now what I'm doing is I'm writing this, each C is C to the half, C to the half. And I'm pushing the first C to the half around to the end. And so I get this. Now, notice that this is a matrix and this is its conjugate transpose, C symmetric, of course. And this is conjugate transpose. So this is just going to be basically the squared norm of this. I haven't written that out explicitly, but so it's going to be the trace of this matrix with its conjugate transpose. And so in particular, this is 0 if and only if this is 0. Okay, and so that's what we're going to work with. We're not going to work with the condition that trace CD is 0. We're going to work with this condition. Okay, so the next thing notice is that the trace of this, well, I can expand U of t as sigma e to the it theta r e sub r. And so I do that and rearrange a bit and I get this. Okay, now the e to the r is posi-semi-definite and C is symmetric, so it follows that this is posi-semi-definite. So that these matrices C, E are posi-semi-definite, and so their eigenvalues are non-negative, and the trace, the sum of the traces of these things, sum over R of these traces. Well, you bring the trace in, well, no, I'm not, I'll leave the trace where it is. I'm going to take the sum of the ERs, that's the identity. And so we get this when we, now, distracting myself. So there's the identity, and so we're looking at the trace of C, but C's identity matrix, so it's 1. So these numbers are non-negative and sum to 1. So they're a probability density. And so it follows that this trace, well, what we've shown is that these guys are non-negative sum to 1. And so this trace is a convex combination of these guys. Now, go back to I don't know why I like changing color, but I will. So there's the unit circle badly drawn. And I've got these eigenvalues, we've got the eigenvalues of e to the I theta RT. Now, when t is 0, they're all equal to 1. So there's the unit circle, and there's a 0 there in the middle one. So at time 0, and as t increases, they're going to spread out. So you can imagine we at some point they might look like this. Now, the point is that this is going to be a multiple of theta 1, and this is going to be a multiple of theta m. And we're going to be in trouble. So what I'm saying is if PQ is, so I'm going to, I guess, basically prove by contradiction. My point is that if the eigenvalues of these EDIT theta r lie on one side of a line, strictly on one side of a line through the center, then their convex hull does not contain the 0 vector. So if you want some convex combination of these guys to be 0, then their convex hull has to contain 0. If they all lie to one side of a line through the line through 0, then there's no convex combination of them equal to 0. Okay, and so the conclusion then is that if this is less than pi, so that these points all lie on an arc of length less than pi, then the trace of PQ is not 0. Okay, and so that's the end of the proof. Okay, so again, it's a geometric argument. We're saying that the eigenvalues of these lie on the unit circle. If they all lie on one side of a line through the origin, no convex combination of them is equal to 0. And so if the trace of PQ is 0, then T must be less than, T must be greater than or equal to pi over theta 1 minus theta m. Now, the theta 1 and theta m lie in your eigenvalue support. You can always assume that theta 1 is the spectral radius, since it's always in the eigenvalue support. And theta m can be the least eigenvalue. Now maybe it's in the eigenvalue support, and maybe the eigenvalue support doesn't contain the least eigenvalue, in which case your bound gets a little better. But the point is we get this bound, and the bound is a bit rough, so I'm not concerned with polishing it up at this this point. And this is a repeated remark I made earlier, that this result applies to state transfer. Now, it is, to me at least, kind of interesting that we don't make any real, the only assumption we make about C and D is their densities. They don't need to be real, they don't need to be pure, they just need to be densities. Now, and if you want to go back and write down for pure states or vertex states, you'll discover the proofs are not really any different, not any easier. Okay, and one moral of this is that generally using density matrices does in general not make things that doesn't make things more difficult. There are odd times where the other formulations make life a little easier, but in general, the density matrices are the easiest approach. And on top of that, you often get more generality. The other comment I should make is that there are versions of this bound found by physicists with names attached, which I don't remember right at this point. So the physicists have more detailed bounds. The point of it, for their point of view, is the question is that if two states are orthogonal, then you can distinguish them exactly by measurements. So you can decide whether the state is state 1 or state 2. So they like having orthogonal states. And so this question about time to orthogonality has some meaning for them. Okay, but I won't be going there. Okay, so we've done that. Okay, so the issue now is to actually get a bound in a period on vertices of a graph. Okay, so we assume X is a graph. The eigenvalue of the vertex, eigenvalue support of the vertex A is theta 1 down to theta m. And then in that case, the minimum period of A is at least 2 pi over theta 1 minus theta m. There might be a way of deriving this directly from the previous lemma, but the proof is only about 3 lines, so we won't fuss. Well, there's some overlap. If A is periodic at time tau, then as we saw above, that EA must be an eigenvector for U of tau with eigenvalue lambda. Okay, and lambda is an eigenvalue of unity matrix, so it's got absolute value 1. So now we multiply both sides of this by E sub r. U tau E sub r is e to the I tau theta r times E sub r. So we get this equal to this. Okay, and so that tells us the eigenvalue is equal to e to the IT theta r. Okay, and so if I take two different eigenvalues, theta r and theta s, then I get this is equal to 1. Okay, and that gives me the bound. Well, I've got it written down here. Stop. Yeah, okay. So we have this, and so then we get that T times theta r minus theta s is some integer multiple of 2 pi. And then that gives us and since MRS is at least 1, we get this. Okay, and so there's a bound. The interesting thing is, as I said, it's not ridiculous. It tells you that if you look at a graph of bounded valency, then you're going to get, if the graph is cubic, then the minimum period is at least 2 pi and 3. If you want to get things faster, this is telling me I would need to increase the valency. Okay, and that's consistent with what we know. Even if you look at cube-like graphs, that's consistent with what we see. Now, on the other hand, if I look at the path on 2 vertices, I get the recurrence time. Actually, no, that's right. The path on 2 vertices, this is tight. Theta 1 is 1, theta m is -1, so you've got 2 pi on 2. So we're good to go. I don't claim it's tight in too many other cases, but still being tight once is a lot better than not being tight at all. And it does seem to be qualitatively the right order. And so the real point then is, can we get something, that more, can we get an improvement on this bound, which is tight infinitely often? Okay, so with the cube-like graphs, I just constructed examples where the minimum period, you can make the minimum period as small as you want. And when in these examples, you observe that the valency is increasing, okay, and that's consistent with this. But the question would be, can we find a tight bound for the minimum period on a cube-like graph? Okay, that's an open question. Yeah, okay, so any questions about that? Okay, so now for time. Actually, I think one thing I want to, I'm going to wrap up now. The next week, is it right? What's the day? Next week is what we laughingly call reading week, and I think that means most of you guys is reading week. And I'm not sure how much reading gets done, but we're not worried about it. So there won't be any lectures next week. Okay, so just warning you. And so you get a week off. Now, if you have questions for me, I'll be around and as usual and stuff. So I mean, I don't get a reading week, and it's not going to bother me if you ask. And so I won't start on the algebraic stage today. I'll stop now. Any questions?